Hi, my name's Blair and I'm from the Faculty of Science at the University of Technology here in Sydney. And today we're going to look at cell biology and genetics. The first subject we're looking at is an introduction to chemical compounds. Here we're going to look at the basic chemistry that underlies the biology of life. This presentation may contain material that is protected under copyright. You may not reproduce or distribute any of this material. This presentation can only be used for your own personal education and learning. The learning objectives of this vodcast is to able to demonstrate an understanding of the link between chemistry and biology, with a focus on essential elements, chemical bonds, water, and carbon. These are the elements in living organisms, including ourselves, humans. There are 96 naturally occurring elements on the planet, 25 of which are essential for life. We are carbon-based organisms. Carbon compounds have a huge diversity, an absolutely huge diversity and variety. Some of which are small, such as less than 30 atoms, some of which are very, very large super macromolecules. Carbon compounds are the building blocks of life. In another vodcast, we're going to look at carbohydrates, and they provide the energy for life. So first we're going to look at chemical bonds, and in this case, ionic. There are two ways in which chemicals can be bonded, and that is ionic, or another one we're going to look at is covalent. Ionic bonds actually involve the transfer of an electron from one element to another. So we're looking at an electron in the outer orbit of an element, and it is actually going to be transferred to the outer orbit of another element. When this happens, one of the elements becomes positive and the other element becomes negative. These bonds, ionic bonds, are not that common in biology. A bond that is common in biology is covalent. And in this case, we're talking about the sharing of electrons. These are common in biology. When we're looking at a covalent bond, we're looking at the sharing of electrons to make a molecule. We are carbon-based organisms. And carbon compounds like sharing electrons. Carbon compounds use covalent bonding. Now, when you've got a covalent bond, we get polarity. Polarity is when we're talking about unequal sharing of electrons. So polarity is unequal sharing of electrons. What we've got here is one element in the molecule becomes slightly negative. The element becomes slightly negative because it is drawing the electrons closer to itself. When one of the elements in a polar molecule becomes slightly negative, the other element becomes slightly positive. This is because the electrons in the polar bond, in the covalent bond, are being drawn away from it towards the other element. The classic example of polarity is water. In water, the oxygen becomes negative and the hydrogen becomes positive. The polarity of water is absolutely essential for life. Just as an aside, notice the geometry, the three-dimensional arrangement of the elements in space. All molecules have a distinctive three-dimensional shape, and this is particularly important in recognition, such as in enzymes and in antibodies. These are things you'll learn about later in your degree. When we've got polarity, we've also got hydrogen bonds. What we're looking at here is the weak attraction between polar molecules. What we're looking at here is where we've got a slightly negative end and a slightly positive end being attracted towards each other. Hydrogen bonds are weak because the molecules need to be close together for an attraction to occur. But this can also lead to repulsion. And that is, for example, if two slightly negative ends of molecules come close together, they will actually repel each other. Now, the surface of the Earth is about 70% water, and therefore we need to understand the chemistry of water in order to understand life. We have to understand how water interacts with itself and with other molecules, compounds, ions, elements. Water is a covalent interaction between oxygen and hydrogen. It is the sharing of electrons. Within water, there are lots and lots of hydrogen bonds. Now, within water, remember that we've got lots and lots of hydrogen bonds. And we need to remember that on the Earth, there's about 70% water, and we as humans are about 60% water. Therefore, we live in an aqueous environment. Therefore, elements in our body, ions, molecules, compounds, need to interact with water. Compounds in our body need to dissolve in water in order for us to be able to use them. Therefore, we're looking at the fact that molecules try to keep their charged or polar regions on the outside of the molecule. By keeping their charged or polar regions on the outside of the molecule, that can interact with water because water is polar. Therefore, compounds that are hydrophobic, uncharged, or non-polar do not dissolve in water. But on the other hand, compounds that are hydrophilic, that are charged, or that are polar, do dissolve in water. Now, we are carbon-based organisms, and carbon has 4 valence electrons. Because carbon has these 4 valence electrons, it has a huge capacity to make a variety of compounds. Now, compounds with carbon can be single bonds, and single bonds rotate in space, or they might be double bonds which don't rotate, And we've also got triple bonds for carbon. Now, carbon can bind to itself, or it can bind to other elements, for example, binding to oxygen or binding to hydrogen. Now, when we're talking about carbon compounds, we have isomers. And isomers are a compound that has the same molecular formula but a different arrangement of those elements in space. Now, for example, we have structural isomers. These are a different arrangement in space. For example, when we do carbohydrates in another vodcast, we have glucose and fructose, which are monosaccharides, and they have the same chemical formula but a different arrangement of the elements in space. Now, we've also got things called cis and trans. Cis has the functional groups on the same side of the double bond, whereas trans has the functional groups on the opposite side of the double bond. Now, then we've also got enantiomers. An enantiomer is a special case of a stereoisomer. And when we're talking about enantiomers, we're talking about handedness. And these are compounds that are the mirror image of each other, but cannot be overlaid. Now, this idea of isomers is important because in biology, shape of a molecule is very important. And that's because in the body, we use shape to recognize things. Now, for example, in other vodcasts, we're going to talk about L and D amino acids, as well as L and D carbohydrates. These are isomers. Carbon compounds, not only do they have a great variety due to the type of bonding that carbons can make, and also the different elements that can be involved, we've also got another way to increase diversity, and this is via functional groups, which are also known as R groups. And functional groups are different groups of elements that have different chemical properties, chemical characteristics. And by adding all these different R groups, which have different chemical characteristics, we increase the diversity of carbon. For example, we have the hydroxyl R group, such as in alcohol or carbohydrates. And we also have the NH2 group, which is in amino acids. So in these vodcasts, we've looked at elements of life, such as carbon, hydrogen, oxygen, nitrogen. We've looked at ionic bonds, which is the transfer of electrons. And we've looked at covalent bonds, which are the sharing of electrons. Polarity, which is where we get slightly, which is delta. We get slightly positive and slightly negative. We've also looked at hydrogen bonds, which is to do with polarity. And we looked at the wide variety of carbon compounds, such as isomers, which are the same chemical formula but a different arrangement in space, and functional groups, which are also known as R groups.